Imagine the universe as a grand cosmic dance, a ballet of planets, moons, and asteroids gracefully moving through the vast expanse of space. Every planet, each with its own unique characteristics, moon, our celestial companion, and asteroid, even the smallest space rock, moving in precise, predictable paths. These paths are not random, they are governed by fundamental laws. This dance is led by gravity, the conductor of this cosmic orchestra, the invisible force guiding each celestial body along its orbit, dictating its speed and position. An orbit is simply the curved path an object takes around something bigger, a continuous loop in the fabric of space, like Earth gracefully circling around the sun. Think of it like a tetherball, a simple game that perfectly illustrates the principles of orbital mechanics. The ball is the planet, constantly pulled inward, the pole is the sun, the massive center of gravity, and gravity is the rope, the unseen connection that keeps everything in place. Orbits aren't perfect circles. They are more complex than that. They're usually ellipses, or stretched-out circles, a subtle deviation that has profound effects. Earth races around the sun at a mind-boggling speed of about 107,000 kilometers per hour, a testament to the immense power of gravity, completing one orbit every 365 days, marking the passage of a year. Understanding orbits is crucial for everything we do in space. It's the foundation upon which all space exploration is built. From launching satellites that connect our world to exploring other planets and pushing the boundaries of human knowledge. So, let's dive into the secrets of these celestial pathways and unlock the mysteries of the cosmos. When we observe objects in space, understanding their movement is key. To accurately describe an orbit, whether it's a planet, a comet, or a satellite, we use 6 key numbers. These numbers are called orbital elements. They act like coordinates in space, defining the path an object takes around another. The semi-major axis is the first element, and it tells us the orbit size. Think of it as the average distance of the orbiting object from the central body it orbits. It defines how far on average the object is from what it orbits. A larger semi-major axis means a larger orbit. Eccentricity is the next element, and it describes the shape of the orbit. An eccentricity of 0 represents a perfect circle. The closer the eccentricity gets to 1, the more stretched out or elongated the ellipse becomes. So, 0 is a perfect circle, closer to 1 is more stretched out. Inclination is the third element, and it measures how tilted the orbit is relative to a reference plane. This reference plane is often the ecliptic, which is the average plane of Earth's orbit around the Sun and by extension the solar system's flat plane. The last 3 elements, argument of periapsis, longitude of ascending node, and time of periapsis passage pinpoint the orbit's orientation in space and specify the object's precise position along that orbit at a particular time. With these 6 elements precisely defined, astronomers and space mission planners can accurately predict where a planet, asteroid, or spacecraft will be at any given time. This predictive power extends far into the future, allowing us to forecast positions and trajectories even decades from now. For example, the Magellan spacecraft's orbit around Venus was carefully chosen and meticulously planned using these orbital elements. This allowed it to systematically map the planet's surface using radar. It's all in the numbers, and the precise application of these orbital elements. That's how we choreograph the cosmic dance of planets and spacecraft, ensuring everything arrives where it needs to be, when it needs to be there. Let's break down some key orbital terms. The closest point in an orbit is periapsis. The farthest is apoapsis. For Earth we call them perigee and apogee. For the Sun, perihelion and aphelion. Objects move fastest at periapsis and slowest at apoapsis. The orbital period is the time it takes to complete one orbit. Earth's is about 365 days. The true anomaly tells us where an object is along its orbit, like a clock hand pointing to its position. Nodes are where an orbit crosses the reference plane. Ascending node goes up, descending node goes down. These terms help us track and predict every move in the cosmic ballet. Satellites, those technological marvels, rely on special orbits to fulfill their diverse missions. These carefully calculated paths dictate how a satellite interacts with our planet. Each orbit is tailored for different jobs, ensuring optimal performance and data collection. From communication relays to scientific observations, the right orbit is crucial. Geosynchronous orbits are particularly fascinating, as they match Earth's rotation perfectly. This means the satellite appears to hover over the same spot on the Earth's surface. As a result, satellites in geosynchronous orbit return to the same spot in the sky each day, making them incredibly useful for continuous monitoring and communication. Geostationary orbits are a specific type of geosynchronous orbit, positioned directly above the equator, providing a stable and consistent vantage point. From our perspective on the ground, these satellites appear motionless, making them perfect for applications like communications and weather satellites, where a fixed connection is essential. On the other hand, polar orbits take satellites on a path that passes over the North and South poles, allowing these satellites to systematically scan the entire planet as they circle the globe. This comprehensive coverage is achieved as Earth rotates beneath them, making polar orbits ideal for mapping, environmental monitoring, and detailed Earth observation. Sun-synchronous orbits are a special type of near-polar orbit, carefully designed to maintain a consistent relationship with the Sun. These orbits cross the equator at the same local solar time each day, ensuring predictable lighting conditions. This consistent lighting is crucial for applications that require uniform imagery, ensuring consistent lighting for images. These clever orbits let us monitor our planet, communicate across vast distances, and explore the universe with unprecedented precision. Each orbit is meticulously designed for a specific purpose, maximizing its effectiveness. This careful planning is what allows us to maximize what we can do from space, pushing the boundaries of technology and exploration. That's orbital engineering in action, a testament to human ingenuity. The sky's not the limit, it's merely a stepping stone. It's just the beginning of our journey into the cosmos. Now let's talk about Lagrange point's 5 special spots where gravity and motion balance perfectly between two large bodies, like the Sun and Earth. Place a spacecraft at 1 and it stays put relative to both bodies. L1 is great for solar observatories. L2, shielded from the Sun, is perfect for telescopes like James Webb. L4 and L5 form stable triangles with Earth and the Sun. Some missions use halo orbits looping paths around these points to stay nearby without using much fuel. Mastering these orbits opens new frontiers, staging posts for Mars missions, parking spots for telescopes, even future space habitats. By learning this cosmic choreography, we're not just watching the universe, we're joining the dance. Subscribe for more cosmic adventures.